Alright students, welcome back to the second part of the linear algebra course for engineering. We will start off where we ended in the first semester. We ended at section 4.4. I require you to just go and revise section 4.1 up until 4.4 again. We will start off with section 4.5, which is on dimension. Alright, so recall that in a vector space, if we're given a set of vectors, v1 up until vn, we say that this set is a basis for a vector space V if both of the following properties hold. So the first property is that S must be linearly independent. Alright, how do we show S is linearly independent? We show that by setting up an equation, and basically the equation looks like this, where specifically k1 up until kn are all real numbers, and we set up that equation, and then we go and solve the real numbers k1 up until kn. And if it happens that the only solution to this equation is for each k to be 0, then we say the set is linearly independent. Okay, so basically so each ki has to be 0 for all I between 1 and n. If that needs to be the only solution, it is called the trivial solution. Then the set S is linearly independent. Alright, and the second property that needs to hold is that S needs to span V. Now what does it mean for S to span V? It means every vector in V is a linear combination of the vectors in S. Okay, so basically what you do is you take a vector from V. Okay, and now we need to find scalars k1, k2 up until kn, such that the following holds. All right, so there that equation needs to hold. So in other words, so basically V is a linear combination of the vectors in S. So if you can find such a solution for each V, then we say that S spans V. Alright, so that brings us to this important theorem, Theorem 1, which is 4.5.2. So if V is a finite dimensional vector space, and V1 up until Vn is a basis, right? Okay, now what is a finite dimensional vector space again? It's a vector space that you can span with finitely many vectors. Okay, and if this let's take any set in V. If a set has more than n vectors, then it has to be linearly dependent. So if the basis in a vector space has got n vectors in it, and you take any set of vectors that's got more than n vectors, then that given set, doesn't matter what it is, it will be linearly dependent. Now, if the set has got fewer than n vectors, then this set will not span V. So the basis actually determines, tells you something. It tells you that if it tells you something about the required number of vectors necessary to span a given vector space, and the required number of vectors that's necessary for that set of vectors to be linearly independent. Okay, so let's just see why this is the case. It's merely an application of solving homogeneous linear systems of equations. Alright, so let's first take a set of vectors W from V of m vectors, w1 up until wm, and each wi comes from v, and the indices I run from 1 up until m. And we specifically require that the set of vectors w has got more than n vectors in it. Alright, so let's k1, k2, and km be up until km be scalars such that that linear combination is equal to 0, and what we want to do now is we want to establish whether w is linearly dependent or linearly independent. We want to show it's linearly dependent. Okay, so how do we do that is remember that the set of vectors v1, this set of vectors here is a basis. So a basis spans the whole vector space V. So we can write every vector as a linear combination of the vectors and the basis. Right, so we can take those W's, W1, W2 up until Wm, and we can all express them as linear combinations of vectors in the basis, which is the set V1, V2 up until Vn. We can set up the following system of equations. Right, so there we're going to set up our system of equations. So there's a system of equations that we can set up, right? So basically what that is right, it's basically all the vectors in W expressed as linear combinations of vectors in the basis. So remember what the equation for a linear combination is. Like these are all scalars. All of these quantities are scalars. And I just labeled them in this particular way. It doesn't really matter how you label them. And each W can be expressed as a linear combination of vectors in the basis. Alright, so all we're going to do now is we're going to take each W and we're going to substitute it. We're going to take W1 and substitute it in there. Okay, we're going to take W2 and substitute it in there. And we're going to do that for all until we get to the last one, and we're going to substitute it in there. Okay, and then we're going to find a new set of equations, and we can simplify and get the following. Right, so as I previously said, you do the substitution and you gather the terms attached to V1, V2 up until Vn, and you get this equation here. Now, we know that V1 up until Vn forms part of a basis, and therefore those vectors must be linearly independent. So what this implies is that this has to be 0. That has to be 0 up until the last term. That coefficient has to be 0. Right, so we can set up a homogeneous linear system which looks as follows. Right, so there we've got our set, our equation, and from that we can set up our linear homogeneous system there. Okay, so now the question is, if we look at this system of equations, all right, so how many equations are there? How many equations are there in that system? Go and count them. There are n equations, right? And how many unknowns are there? There are m unknowns. Okay, now in an equation, now what did we say initially? We said initially, we assumed what? We assumed that m is strictly bigger than n. Okay, so we've got a set of equations here that's got more unknowns. It's got m unknowns, and there are n equations. So it's a homogeneous linear system with more unknowns than equations. And what do we know about such a homogeneous linear system? Such a homogeneous linear system must have infinitely many solutions. All right, so it's at least got more than one solution. So remember now, these k's are my unknowns, right? So if I've got more than one solution for these k's, if we go back to this equation here, okay. Now, what needs to happen for the set W to be linearly independent? We need these k's to be 0 and 0 only. Now, if you've got more than one solution, it means there's a non-trivial solution to that equation. So what's the implication of that? The implication of that is that the set of vectors W must be linearly dependent. All right, so that linear system, the linear system has more unknowns. It has more unknowns than equations. All right, so and the unknowns here are these k's, right? There are those k's there. Okay, so that equation, the original linear independence equation, has a non-trivial solution for K1 up until Km. So what's the conclusion? The set W cannot be linearly independent. Okay, so W is linearly dependent. So now we look at the second part, which is very similar to the first part. So now let's see if W has fewer than n vectors. What happens to the span? Can W span the whole vector space V? All right, so again take the set W, but now let's require that the number of vectors is strictly less than n, and n denotes the number of vectors in the basis. All right, so let's take n scalars, and we set up that equation, K1V1 plus K2V2 plus up until KNVN equals to 0, right? So let's see what solutions we can get for these Ks. Now again, we apply the same principle. What we're going to do is we want to eventually show that W cannot span V. Well, let's assume that W can span V. Alright, so let's assume W spans V. Then we can set up the following system of equations. What it means now is that we can express every vector in V as a linear combination of vectors in W. Okay, so let us set up my system of equations. So because we can write every vector in V as a linear combination of vectors in W. Right, so there we've got our linear combination expressions, right? Okay, so so there we've got all our equations, and remember now we said that W spans V, so I can write every V as a linear combination between vectors in W. Okay, and I can do that. So all these K's are just pretty much scalars. Okay, so they are all scalars, all of them. Okay, and now that we have our linear combinations, again we follow the same procedure. Let's take this V1 and plug it in there. Let's take that V2, plug it in there, carry this process through for all my V's until I get to the last V, and I plug it in there. Okay, and now we are going to again get a system of equations that look as follows. Alright, so there, gathering all the W1 terms, W2 terms up until Wn terms, we get an equation in terms of the vectors W1, W2 up until Wm. And now what I'm going to do is I'm going to set up another system of equations that I want to solve. Okay, so now that we have those equations, we can go and set up the following. So we can take that equation and we can set that equals to 0 and see what we get. So we can do that. Right, there we go, a second equation. And we can set that equals to 0, and then we can go on and do that for all. Okay, so there we've got our final equation, and we're going to set that equals to 0. And now let's see again. Now again, what do you have? You've got a system, a homogeneous linear system. How many equations does this system have? It's got m equations, and how many unknowns does it have? It's got n unknowns. Remember, these are all my unknowns, and my number of equations is m. Now I've got more unknowns than equations, and a homogeneous linear system that's got more unknowns than equations, it's got non-trivial solutions. It's got at least one non-trivial solution. So if we go back and we look at this equation here, it turns out that I can find non-trivial values for k. So what's that going to imply? It's going to imply that my V's are not linearly independent. Right, so as I previously said, the system has got more unknowns than equations, and therefore we're going to find a non-trivial solution for the k's, for k1, k2 up until kn, and therefore it contradicts the fact that v1, v2 up until vn are in fact linearly independent, because we can find a non-trivial solution for the k's. So therefore, if you have a set of fewer vectors than the basis, then that set cannot span the whole vector space V. Okay, now we asked to apply that theorem. So show by inspection that the following sets are not bases for the respective spaces. Okay. Now, if we look at P2, now P2 is all the polynomials that have a degree at most 2. Now, now we know that the standard basis for P2, the standard basis there is the set B, where B is 1x and x squared. Okay, so the standard basis has got 3 vectors in it. So apply the previous theorem. If you've got a set S that's got more vectors than the number of vectors in the basis, then P2, that set S, is not as linearly dependent. So obviously S in that case cannot be a basis. Now in R3, what is the standard basis there? In R3, the standard basis is basically comprised of the standard unit vectors. Right, we've got that 0, and the last vector there is the vector 0, 0, 1. Okay, and that standard basis there's got 3 vectors in it. Clearly S has got 2, so S has got fewer vectors than the standard basis. That's going to imply that my set S can definitely not span R3, so it's not a basis. What about the last one? The last one is the set S of 2 by 2 matrices given there. Now, what is the standard basis for M22? We know the answer to this question. The standard basis there is these matrices here. Okay, it's 0, 1, 0, 0, 0, 0, 1, 0, and the last one is 0, 0, 0, 1. Okay, so there are 4 vectors in that basis. So clearly S can definitely not span the whole M22 because it's got fewer vectors than the basis. All right, so none of those sets can be bases. All right, next slide, we've got Theorem 2, which is Theorem 4.5.1. What this theorem says is all bases for a finite dimensional vector space have the same number of vectors. So you can choose any 2 bases. These bases can be completely different from one another. They always will have the same number of vectors. Right, so if one basis has got n vectors, then any other basis will have n vectors. So why is this the case? Well, we can look at quickly at the following proof. So you can take a basis to have n vectors, right, for the vector space V. And let's take another basis S, and let's say it's got R vectors. Right, and it's also a basis for V. So what we need to show is that the number of vectors in S is the same as the number of vectors in B. Okay, so now we apply our previous theorem, which says that if you've got more than, if you go back to our previous theorem, if you've got more than n vectors, that set is going to be linearly dependent. Right, so what that then tells us is if the number of vectors in S is more than the number of vectors in B, then we know that S is going to be a linearly dependent set, which is impossible because S is a basis. Also, the other way around, if S has got fewer vectors than B, then S can definitely not span V. Well, that's going to contradict the fact that S is a basis, because a basis has to span V and it has to be linearly independent. So that's literally going to force the number of vectors in S to be the same as the number of vectors in B. Okay, so that's a very simple application of this theorem. So that brings us to the concept of dimension. So in a vector space V, we say that V is finite dimensional if it has a finite basis. We know that from section 4.4. And again, if it's got if you cannot span it with finitely many vectors, we say it's infinitely dimensional. Now, what is the dimension? The dimension of a finite dimensional vector space V is denoted by the dim of V, and it's defined to be the number of vectors in a basis for V. All right, now if a vector space only has the zero vector, by definition, we say that the dimension of the set containing only the zero vector is 0. Remember that the zero vector, if a set only contains a zero vector, it's not very interesting to work with a set, because that linear independence requirement doesn't work so well, because you can find non-trivial solutions to that equation. So by definition, the dimension of a vector space only containing the zero vector is 0. Okay, now in this example, they ask us to find the dimensions of the following spaces. So if we look at Rn, how many vectors does this how many vectors? Well, it helps to look at the standard basis. What's the standard basis for Rn? The standard basis for Rn, remember, is all these unit vectors. Right, now I'm not going to write this all out. All these unit vectors. Okay, and you let the one run over all the components, and you make all the other components 0. Okay, and you go on until you have a 1 in the last position. Okay, so that is, how many vectors are there? Well, the 1 can take on n positions, so B has got n B has got n vectors. So the dimension of Rn is n. Standard basis for Pn. Pn is all the polynomials of degree at most n. So that is going to have how many vectors? It's going to have n plus 1 vectors. So the dimension of Pn is n plus 1. And how many vectors? Okay, so what is the dimension of the vector space M subscript Mn? So again, look at the standard basis. What is the set M subscript Mn? It's all matrices with m rows and n columns. So the standard basis there will be all matrices that have got zeros everywhere, except for one position, and that one position has a 1 in it. Okay, and it's all m by n matrices. All right, so the standard basis for M subscript Mn is pretty much this set here. Okay, so it's all these matrices that's got a 1. It's all the matrices that's got a 1 in a particular position and 0 everywhere else. So these ones, they run through all the rows and the columns until you get there to the last row and the last column. Now, if we had to count the number of vectors in B, pretty much all the positions that can be taken on by 1, there are exactly m times n such positions. So basically, the cardinality of B, in other words, the number of vectors in B, is m times n. Okay, and that is going to imply that the dimension of mn is going to be m times n. Okay, so that is that completes the first. All right, let's look at the next one. Let's look at the solution space of Ax equals 0. So the solution space, all solution vectors to that linear system. So let's look at the first one. Right, so there we've got our system. Remember, this is the vector x. That is the matrix A. And that is the vector 0. Right, so from there we can establish the equations we need to solve. So our solution space then becomes, okay, solving for z, y, and x. And that is just where t is a real number, okay? And so my solution space is, okay, my solution space then becomes, okay, so it's all vectors of the form, pretty much scalar multiples of the vectors -4, -2, and 1. So what is the dimension of this solution space? Well, what we need to do is we need to find a basis for the solution space S. Okay, and to do that, look at what the solution space looks like. We need to find a basis for the solution space S, and it's easy to do that because we can just pick the vector -4, -2, and 1. -2 and 1. Now, why is this a basis? Because the vector in B, the vector -4, -2, 1 is linearly independent. You can solve the equation. You can solve the equation K1 -4, -2, and 1. And the only solution to that equation is when K1 is 0. Okay, so K1 has to be 0. So any set of a non-zero vector, any set with one non-zero vector is always going to be linearly independent. All we need to check is that the set B spans the set S. Look at the set S. S is just a linear combination of the vector -4, -2, 1. So therefore it's easy to see that the span of B is clearly S. So therefore the basis for S is this vector -4, -2, 1. So what is the dimension of S? The dimension of S is the number of vectors in my basis, which is in this case 1. Alright, so next we have the second problem of question 2. So there we've got our matrix equation that we set up, and from there we can deduce the following. Right, we can set up this homogeneous linear system of equations there. Okay, and from that it follows that we can solve for y and x as 0. All right, so what does what is the dimension of the solution space? Firstly, what is the solution space? Right, from that we can solve the solution space as the set of all vectors that look like this. The x component is 0, the y component is 0, and the z component is 0. Okay, so that's one single vector. So therefore S is the set that contains the 0 vector. And therefore we know any set consisting only of the 0 vector, the dimension of that set we know is by definition it's 0. Alright, so let's look at the last one. So again, that's my matrix A, that is my vector x, and that is my 0 vector. Okay. Alright, so from there we have that that x is 0, that y, again we have to parameterize y and z. Okay, and S and T are both any real numbers. So the solution space becomes the set S, which is the set of all vectors of the form 0, S, T. Okay, and S and T are real numbers. So the question now is, what we need to find a basis for S. Now if you look at the vector 0, ST, you can write that as a linear combination that looks as follows. It's the vector 0, 1, 0, okay, times a scalar multiple, which is S, plus, you can write that as a scalar multiple of the vector T times the standard unit vector. Okay, so that gives you a clue as to what my basis needs to look like, what my basis needs to be. So what I'm going to do is I'm going to choose B as the set containing two vectors, this standard unit vector and the other standard unit vector 0, 0, 1. Now, first of all, does B span S? In other words, can I write the vector in S as a linear combination of the vectors in B? And the answer is yes, there is a linear combination. Right, so I can write any vector in S, 0st, I can write it as a linear combination between the vectors in B. Okay, so that's one thing. So clearly from that, the span of B is clearly S. So all I need to do now is I need to show that B is linearly independent. All right, setting up our linear independence equation. K1 times 0, 1, 0 plus K2 times 0, 0, 1 equals to 0 vector. You can solve that and get K1 equals 0 and K2 equals 0. So therefore it's a linearly independent set. So therefore B is a basis for S. And because B has got two vectors in it, we have that the dimension of S is equal to 2. Okay, so let's look at my last one, number 3. There we have in R3, we've got the set S comprising of all vectors where the sum of the x, y, and z component all adds up to 0. So is that what is the dimension of that set S? Right, so we take the set S, and the set S is basically equivalent to the set of all points A, B, C, where A is equal to minus B minus C, and therefore that's just the same as all the points X, Y, Z, where X component is minus B minus C, the Y component is B, and the Z component is C. And now we have the following. Right, so if we look at this vector, and we look at this, we can write this vector minus B minus C, B, C as the sum between these two vectors here. Okay, and then we can basically go and note that that basically B times minus 1, 1, 0, okay, plus C times minus 1, 0, 1, adding those two vectors gives me this vector here. Right, so we get that sum there, that linear combination. So So basically the span of these two vectors, which is all the linear combinations of those two vectors, is equal to S. So that gives us a clue as to what the basis must look like. So if we take B to be the set of those two vectors, you can note that those two vectors are linearly independent. Because again, the same story. If you take K1 multiplied by -1, and you take K2 and you multiply that with the vector -1, 0, 1, you can easily see that setting up your system of equations will lead to K1 being 0 and K2 being 0. Quickly set up the system of equations, and those are your three equations, which will clearly show that K1 and K2 is 0. So therefore, those two vectors are linearly independent, and therefore this set comprising of the two vectors -1, 1, 0 and -1, 0, 1, that's clearly a basis. And since there are two vectors in it, the dimension of S is 2. Right, so next we have Theorem 3, which is the plus-minus theorem. And it's a very important theorem. So if S is a non-empty subset of a vector space V, then the plus-minus theorem states that if S is a linearly independent set, and there's a vector V and in V outside of the span of S, then you can just go and add the vector V to the set S, and the resulting set will still be linearly independent. Likewise, if V is a vector in S and V is expressible as a linear combination of the other vectors in S, then you can take the vector V in S and you can remove it from S, and the span of this new set that you took the old one and you removed V from is the same as the span of the original set S. So you can, in the first instance, you can keep adding vectors to the set S, provided that these vectors lie outside of the span of S. And in the second one, you can keep removing vectors from S, and you will not influence the spanning set, provided that the vectors that you remove are linear combinations of other vectors in the set S. All right, so let's quickly look at why that is the case. So what I'm going to do is first assume S is a linearly independent set, and let's take a vector that lies outside of the span of S. Now what we're going to do now is we're going to take the scalars K1, K2 up until Kn plus 1, and we're going to do the following. Right, now I didn't say this, but just take note that S is a set of vectors V1 up until Vn, and we are going to set up the equation I talked about. So, we're going to take scalars K1 up until Kn plus 1, and we're going to set up this linear independence equation, right? So there's that equation. And now we want to know what is going to happen with these scalars. Okay, so let's look first at the first case. Right, so let's assume first that Kn plus 1 is not 0. Well, then it turns out that you can solve for V in terms of all the other vectors. So you can solve for V as, well, V essentially becomes a linear combination between the vectors V1 up until Vn. But this implies that V is in the span of S. But we said previously that V is not in the span of S. There we go, right? So therefore, we have a contradiction. So it implies that kn plus 1 must be 0. Right, so what is the implication of that? We can say then that kn plus 1 is 0. So going back to this equation then, it is then easy to see that that last term there right, let's just do it properly. That term falls away. It falls away. Okay, so all you basically left with is this equation equals to 0, and we know that S is linearly independent. So therefore K1, K2 up until Kn are all 0. So therefore this set is of vectors is linearly independent. Right, so the implication of that is that the set S that you take and you throw the vector V in is linearly independent. Okay, let's look at the second part. V is a vector in S, and V is expressible. Again, S is the set of vectors V1 up until Vn. And let's say V is a vector in S, and V is expressible as a linear combination of the other vectors in S. Then we claim that the span of S is the same as the span of the vector set that I take, which is S, and I remove the vector V from it. Right, so so let us assume that the span of S is not equal to the span of S minus V. Span of S is all linear combinations of vectors in S, and the span of S minus V is all linear combinations of vectors in S minus V. Now, right, so basically let's suppose there's a vector in S, in the span of S, but it's not in the span of S minus V. And remember that S is that set of vectors V1, V2, up until Vn. So what we can do for argument's sake is you can let the vector V just be the nth vector. Okay, and so we can say let V be Vn. Okay, so let V be Vn, and let's take a vector V prime that's in the span of S, but it's not in the span of S minus V. Now, what does it mean for it to be in the span of S? It means that it is expressible as a linear combination of the vectors in S. And what does it mean for V prime to not be in the span of S minus V? It means it's not a linear combination of the vectors in S minus V. Okay, so we can we can basically now go and express V as a linear combination of vectors in S because it's in the span of S. So remember these are the vectors in S, okay? And right, and what did we say about V? We said V is expressible as a linear combination of all the other vectors in S. All right, so we can express V as a linear combination of all the other vectors in S. Okay, and then we said that vector there's V, and we can express it as a linear combination of all the other. Now, what we're going to do now is take V, and we're going to just plug it in there, and basically get the following. So let's do the substitution as I explained. Again, you take that do that substitution, plug it in there, and we're going to get the following. We're going to get the following, right? So I'm just going to make that a little bit bigger. And plugging it in, we get a new expression for V prime, and that is the term that I plugged in. And then simplifying, we get that I've just expressed V prime as a linear combination of vectors v1, v2 up until vn minus 1. And this means that v, the vector v prime, is in fact in the span of S minus V. Okay, so what have I shown? What have I shown? I've taken a vector that lies in the span of S, and remember originally we assumed that V is not in the span of S minus V, but here I'm showing that it is in fact in the span of S minus V, so therefore we get a contradiction. Alright, so this is a clearly a contradiction. This is a contradiction. Okay, so that is a contradiction. All right, so that proves the plus-minus theorem.